Hello everyone, my name is Deniz Sönmez and I'm a computer science major. Today I will be presenting and explaining my Physics 101 project. The aim of this project is to investigate the relationship between force and displacement in a spring system. By conducting experimental measurements, we aim to observe how real-world behavior may differ from the ideal linear model described by the Hooke's law. Additionally, this project seeks to analyze the nonlinear characteristics that emerge at larger displacements. To conduct the experiment, I need a spring, a dynamometer, and an air table equipped with two pucks. I start my experiment by measuring the relaxed length of the spring. After measuring the relaxed length of the spring, I connect the pucks with my spring. Then I attach my dynamometer to the puck on the air table. After this step, I start to collect the force and displacement data. Since I only want to measure the force from the spring and no other forces, I'm using the air table to minimize the friction of the pucks by eliminating static friction. When we first learn about springs, we hear that the force they exert is proportional to their stretch. According to Hooke's law, F equals kx, where k is the spring constant. However, this is only an approximation that works for small displacements. In reality, the force a spring exerts can be better described by a power series. Because there is no force when the spring isn't stretched, the constant term disappears. For small stretches, higher order terms like x squared and x cubed are negligible, and the spring behaves linearly with a constant k. But for larger displacements, the nonlinear terms like higher order terms become important, and the force-stretch relationships curves away from a straight line. Hence, k is truly constant only near equilibrium. For bigger stretches, if we want a better model, a better approximation, we need to add terms like k sub 2 x squared to capture the nonlinearity. Even then, it's only an approximation, and real-world behavior becomes harder to predict as the spring stretches more. But we can see that second-degree polynomial representation is way more accurate than the first-degree representation of the spring constant. By calculating the exerted force more accurately using higher-degree polynomials, we can observe in the energy displacement graph that the potential energy calculated for the spring converges more closely to the actual work done by the force. This shows that determining the exerted force more precisely provides much more accurate information about the energy stored in the spring.